Good afternoon, ladies and gents. We're just doing a final few tests to do with the audio. Just waiting to get the thumbs up from Miss Morrissey to see if we're live. You can hear me loud and clear. Mr. Menza coming from 10:11. We will be starting in about 5 to 7 minutes. Okay, good afternoon, Year 11. We're just about to get started. I'm just going to wait for the thumbs up from Miss Morrissey to know that it's all systems go. You can hear me, Miss Morrissey? Yeah. Okay. I imagine this is going to take about an hour and a half to get through. Sorry, I'm just clipping my mic onto myself. I imagine it's going to take about an hour and a half to get through. You can see it's obviously through paper one, which you've got tomorrow after your maths exam. Sorry, that's my flipping phone going off. It's no good. I'm very much apologising for that. We have paper one here then. So this includes hazards, ecosystems, coasts and rivers. I'm going to be going through the entire course and it will take about an hour and a half. I will be pausing through each section. So every time that I've completed a section, which I'm circling now, I will be pausing. Throughout the live stream, you are able to actually give comments down in the comments section there. Miss Morrissey is working on the computer now, so if there are any questions, please send them forward. And at an appropriate position, I will stop and answer them as best as I can. If you have any technical issues, just give us a shout on the chat if my voice isn't very clear. We've got another live stream set up as well, so we can kind of hear what's going on as well, but please do just let us know what's going on. Anyway, let's get started. So to begin with, we're looking at tectonic hazards. I've got a GIF there for you, which I put in a little bit earlier today. And to begin with, we're starting off with what factors affects the hazard risk. And the first one we need to go through is location. If you happen to live anywhere along a plate boundary here, quite evidently you're going to be at risk of an earthquake. Whereas if you aren't living on a plate boundary, you are less likely at risk of that hazard. The next factor which affects risk is population density. We can see here India, the density there is quite high compared to somewhere like Australia. Now, if there's lots of people living in an area, let's imagine that you are in India, for example, and you're living in some slums. The slums may be built right next to each other as so. If there is an earthquake or a natural disaster, if one house falls over, the rest of them may fall over, meaning a high population density is going to increase the hazard, the risk that you are of living there. Climate is another one there to do with atmospheric circulation or the hurricanes that we're going to experience. And finally, the wealth of a country. That massively impacts the risk that you experience. If you're from a high-income country, you can see the blue countries highlighted here, you have more money, therefore you're less likely to be able to be at risk of a hazard. Unlike if you're from a poorer country, an LIC or some NEEs, where you are more likely to be at risk. So let's get started within the structure of the Earth. And we all know that the inner core is at the centre of the Earth, followed by the outer core. Now, the two that you need to be most familiar with is this one, which is called the mantle. And we are aware that the mantle is made of magma, liquid rock. And finally then, the crust on the very outer part of the Earth is made, crust, that is made of rock. And with those layers of the Earth, if I just redraw them here, we know that we have the mantle, which is made of that liquid, like I just showed you there. And then the rocky crust sits on top. The rocky crust, though, isn't one smooth layer as so. It is actually broken up into what we call different plate tectonics. Now, the best way to imagine this is if you went to the swimming pool. Imagine that you went to the swimming pool one day and you were sat on a float. When you were sat on that float, nobody else is in the pool with you. My question to you is, would the float move? And the answer is yes, because the water beneath you would be moving ever so slowly, meaning that your float would also move one of two directions. Imagine then that someone came to join you and they're also on a float next to you. These floats are going to do one of three things. The first thing these floats might do is they may move apart. This would be called a constructive plate boundary. The plates may also move past one another, as so. This was called friction, and this is called a conservative plate margin. Finally, we all know the big one, which is a destructive plate margin, where that oceanic plate sinks beneath the continental. I'm going to come back to these in a little bit. You may be asked a basic question that asks you to outline or explain something along the lines of convection currents. Convection currents are these movements of the water in our example, or this movement of the magma, where the magma rises and falls due to the heat. These are called convection currents. And to make that a little bit clearer for you, I've also got a diagram here. You can see the mantle there, the very, very large sections underneath the Earth's surface, and you've got the crust, which is much, much thinner. That magma is rising underneath the Earth's surface and then falling back down, and that circulation happens again and again, and then the plates move above. The names of each plate boundary, I've just been through that, but we will be going through it again. The first one here on the top left, we can see that two plates are clearly moving apart. We call this a constructive plate boundary. The next one here, slightly underneath, these are two plates moving past one another. Note how these plates are moving in the same direction. However, this plate on the right-hand side is moving faster, therefore they are still rubbing past one another. This is called a conservative plate margin. And then the last one, like we said before, this is a destructive plate margin. From the images, hopefully you can begin to tell what different processes happen at each plate boundary, but I am going to go through that now with you. At a constructive plate margin, we do have volcanoes. We also do have earthquakes at this plate boundary, but they are very, very minor, and it's not something I would be too worried about at the moment in remembering. However, this plate boundary is where we do certainly get earthquakes at a conservative plate margin. There is lots of friction that occurs there, and I'm going to go through again that shortly. Finally, you also get earthquakes and volcanoes at a destructive plate margin. Earthquakes and volcanoes. Now some people will go, sir, you mean you get volcanoes at both plate boundaries? Yeah. These volcanoes are shield volcanoes. Let me spell shield correctly. And these ones are composite volcanoes. And I do believe I've got a few slides in a while to go through those. So the difference between a shield and a composite volcano. Here are two pictures. Quite clearly you can see this one on the left-hand side is, funnily enough, in the shape of a shield. This one is much more pointy, and this is a composite. Reminding ourselves that this is a destructive plate boundary, and this is at a constructive plate boundary. You can see that the shield volcano is much, much wider. It's got gentle slopes, whereas the composite volcano, it's more narrow and with steep-sided slopes. The shield volcano has a gentle eruption that is non-violent, and the composite volcano has a very violent eruption. Features of volcano. Before we do this, I quickly want to go through with you the formation. So just ignore this now for a second. If we go through the formation of a composite volcano. Feel free to rewind the video and go through this. I'm only going to go through it once. You have oceanic plate, which meets continental plate. Because the oceanic plate is denser, that means heavier, that doesn't sink. We say it subducts it subducts beneath the continental plate. And because it's so warm underneath that surface, this begins to melt in what we call a magma chamber. Now, as pressure rises, this magma forces its way up the centre and it creates what we call a main vent. After years and years, and I'm talking hundreds and thousands of years sometimes, this magma forces its way up the main vent. This is the main vent here. And outside of the crater at the very top. Once that magma has come out of the crater at the top and you can visually see it, it is now called lava, and that runs down the side of the volcano. So when you can see the magma, it is called lava because it is cooling down. You also get gas, ash, steam and dust that comes out, and more importantly, those things that we always remember, those big, big rock bombs that come out. Rock bombs, also known, you might see them written down as volcanic bombs. If you're very lucky, if you're asked to label a diagram, sometimes there's a secondary vent there and a secondary crater on the side of the volcano, and it can also escape out of there. To quickly go through one final time, we have a bit of a clearer diagram. Down here, A, we have the magma chamber. I keep wanting to say magna is in the science place there in Sheffield. You've got the main vent. Here we can see the rock bombs which are coming out on E. These are rock bombs. This is pointing at the crater, C for crater. D would be ash, gas, steam, dust. F, this is a secondary vent and a secondary crater. Secondary vent / crater. We've got here layers of ash and dust that have solidified. So these are different layers of ash / lava and dust which has settled over hundreds and thousands of years and built up that. And this here, G, is lava flow. What are the benefits of living near a volcano? Benefits of living near a volcano then. Why on earth would you want to live near that? Look at it, it's exploding. A few reasons. First of all, tourism. People want to live there because they may have walkers going up here. Here's some walkers walking up the volcano. But you may decide to set up a stall here. This is my attempt of drawing a stall. And you might sell bottles of water, or you may sell souvenirs, because then tourism, that will then generate an income. That means then you can pay tax. That means then the area can improve through education and healthcare. In fertile soils, when all this gas, ash, steam and dust falls, the soils around a volcano can become really, really rich with lots of minerals. Therefore, farmers can grow their crops. So let's add that on here. Farmers can grow crops. Again, that will generate an income for them. They can also sell it. They can eat it. Geothermal energy. We know if there's a volcano here quite near the surface of the earth, there's going to be a magma chamber nearby. Magma chamber. Now that's going to radiate heat through the ground. So what people tend to do sometimes near volcanoes is they build a big factory there. And what they do is they send a pipe down, up and across, as so. And what they do is they pump cold water down that pipe. While the water is underground, because this heat is radiating through, that actually warms up. I'm going to do red water just to show you that it's warming up. And that warm water comes back up as steam then. That steam turns a generator and that produces renewable energy. So actually, you don't really need that pipe there. Earthquake, key terms. If we remember, earthquakes occur at they occur at all three, but I'm going to go through how they occur at a conservative plate margin. There could be a classic question that just asks you to perhaps label a diagram. Now, if we're looking at this side on, what I want you to imagine is this plate on the right, we'll call this plate A. This plate on the right is going into your screen, so it's going away from you. Whereas this plate on the left is coming towards you, out of your screen. So they're rubbing past one another. You can quite clearly see that they aren't very smooth. They have got caught though, just about there. And where they get caught, we call this the focus. Because eventually, when these plates slip past one another, they are going to slip past each other at the focus, and this is where the energy is going to be released. And we don't call them sound waves, we call them seismic waves. And you can see me drawing them on here like that. These are called seismic waves. They're a bit like sound waves, but they're the vibrations in the earth. But we don't call them vibrations, we call them seismic waves. Now, the first place on the Earth's surface to feel these vibrations will be here, directly above it. And we call this the epicenter. They're near enough the only key terms you need to know with the formation of an earthquake. I am just going to show you one example, though, of how you might be asked to use these. If we take this box as example 1, I'm going to draw example 2 now. You've got another conservative plate boundary, as so. This time, though, hopefully you can see the difference. The focus is much shallower here. Epicenter's there. And my question to you, hopefully at home you're screaming at your computers because you're all eager beavers. Let's imagine that that is 30 miles deep, but this is only 2 miles deep. You are correct. If there was a house there and a house there, the house in example 2 would be much worse because it is shallower, therefore it would experience more severe shock waves. That is bearing in mind if we are presuming that they are both measuring the same on the Richter scale, 8.0 for example. A bit of a clearer diagram there for you, rather than my messy drawing. You can see here, 2 plates moving past one another. They've got caught at the focus. This is the fault line, just that line between the 2 plates. The epicenter in the village which would be hurt, and the red lines representing the seismic waves there. Then it moves on to the primary and secondary effects of an earthquake. A primary effect, I always like to remind myself, I went to primary school before secondary school, so primary effects happen first. They happen or occur during the earthquake. During the earthquake or later during the tropical storm when we get to that. The secondary effect, on the other hand, happens, yes it does, I can hear you saying it at home, happens as a result of the primary effects. That was Mr. Knowles making an entrance there. Happens as a result of the primary effects. You will need to know the different effects of an earthquake, all right? We learnt about 2 different earthquakes, and the exam board do ask you to learn 2 contrasting areas. So to go through that very quickly with you. What was your example of an earthquake in a HIC? We learnt about Italy in 2009, and your example of an earthquake in an LIC would be Gorka, Nepal, 2015. Now I'm going to show you here some primary and secondary effects, and straight away some of you are going to be thinking, oh sir, I can't quite remember all of those different effects, there's just so many. Don't worry, you don't actually have to remember them all. I'm going to tell you an easy way how to make it up shortly. But if we just go through these primary effects, 308 people died. Some patients evacuated from hospital. I'm just going to remember those 2. There's more there, several university buildings collapsed, 11 million worth of damage. But I'm personally just going to remember these 2. Now, if we know that Gorka, Nepal is a LIC, presumably more people are going to have died. So in the exam, if you can't quite remember, make up a number. Obviously, you're not going to say 2 billion people died, but as long as you get it in roughly the right region, you will be credited on that answer. So let's have a look. There we go. 9,000 people died. So straight away, try not to look at the rest of it yet. Straight away, we've got a clear comparison there. We have 308 people died in Italy compared to 9,000 in Nepal. And now look at this one. Some patients evacuated from hospital, whereas 26 hospitals in total, 26 entire hospitals were destroyed. Now, hopefully you can pick it up and say, gosh, you know, that clearly isn't, that's clearly quite a significant difference. In Italy, because they have better infrastructure, better building regulations, most people, all right, they only had to evacuate some, compared to Nepal, where 26 hospitals were completely destroyed. That would have had a much more significant impact. And that will have been due to lack of building regulations, perhaps poor infrastructure. They can't afford earthquake-proof buildings, but I will be coming back to that. Let's look at the secondary effects again. So I can't quite remember. Well, let's just go through it a little bit slowly. This one. Tourism fell slightly. Afterwards, the secondary effects in Italy, tourism fell slightly. Well, let's have a look at, compare that to Nepal. In Nepal, gosh, nearly 9% of their GDP suffered because tourism is such a big industry in Nepal. Other ones, look at this, food shortages, loss of crops, reducing income. And only, oh gosh, look at that, number of students at university had decreased. So if you want, do just pause the video at this stage and just think to yourself, if I get asked a question to do with earthquakes and perhaps contrasting levels of wealth, you learnt about Italy and Nepal and just try to remember roughly in the region. So even if you say a couple of hundred people died compared to a few thousand people, if you use those words, you would still get the marks because you have recognised that there is a difference between the LIC and the HIC. I'll just remind you, Miss Morrissey is on the computer, so if you've got any questions about any of this, please do just shoot them her way. You also need to know the comparison between the responses of these. So if we just show you some photographs here, we can clearly see that schools have been destroyed. Look at those. Look at that road there on the right-hand side, top right. It's terrible. The road has been completely and utterly, I'm going to say bamboozled then, that's not the right word. It's irreparable. And then I've also got ambulances down here. Now I don't think I've got this slide, superb, so I'm going to do this from my memory. But in Italy, we know that there was around 25 ambulances which responded. Now let's just think about Nepal for a second. We've got a picture here, Nepal. So, right, that looks like a school to me. So temporary schools set up. That wasn't really necessary in Italy because the schools were absolutely fine. What else happened in Italy? Well, they provided free bus services to people who were affected. There was a free bus service. Whereas Nepal couldn't have that. Look at their roads. They didn't have the infrastructure. Nepal, though, was sent with search and rescue teams. Search and rescue teams because so many buildings collapsed, whereas in Italy, a lot more of them withstood that. If you would like me to go through that a little bit further, please do send a message to Miss Morrissey. I will do that a little bit later on, but I'm going to move on for now. To do with managing earthquakes then, I'm not going to go through volcanoes, you only need to know one. We'll go through earthquakes. You've got this, an earthquake survival kit, and you also have an earthquake-proof building. An earthquake survival kit, you might include there torches, you might include duct tape to strap anything up. We might include a first aid kit. You might include canned food that's non-perishable. You might include bottled water. You might include a whistle. Now it's great being able to name these, but if you can say canned food, because canned food will not go off, a whistle to attract attention if I am trapped, or bottled water because the water supply may become contaminated, aren't they much stronger answers than just saying, I would include a whistle in my earthquake survival kit? You've got an earthquake-proof building here, lots of different things here you've got going on. You've got cross bracing. cross bracing there to strengthen the sides of the building. You have weights on top of the building to counteract the balance. You've got shock absorbers down below. Shock absorbers. You could have sprinklers inside to put out fires. Lots of different bits and pieces that you could have there. The one thing, so I'm just going to go back now. I'm going to go back to the earthquake survival kit. One more thing I just want to say on this is think about if your earthquake survival kit would be different if you were in an LIC compared to a HIC. I did this with a class not too long ago, and we had a discussion around tents. Some people said they'd include a tent in their earthquake survival kit. I said, well, why? And they said, because I wouldn't have anywhere to stay. I said, well, what happens if you're in Italy? And they said, oh yeah, you might get put in a hotel there. Yeah, you might, because they have the infrastructure to do so. I am just going to pause there for about 2 minutes while I have a drink of water. I'm just going to lower the mic. If you've got any questions, send them Miss Morrissey's way. And we're back, I think. Oh, are we? Are we back on, Miss Morrissey? Luke Murray, I can see you on the chat. Well done. How does latitude influence climate? So, what we have here is, I want to draw the sun there. This is moving on to atmospheric hazards, ladies and gents. If we have the sun there, and let's say we have the Earth about here. Now we know that we receive radiation from the sun. Let's change this to yellow to make it orange. So the radiation from the sun is coming in at an angle as so. Now we can see that the equator there of Earth is being hit directly. Whereas, if we look now, can you see how a much larger area of land is covered? It's quite difficult to see on that bit, but I'm going to show you a better diagram in a second. What I'm getting at here, ladies and gents, is the equator is warm because it's hit directly by the sun. Do not say because it is closer. Even though you are technically correct, you would never ever get the mark. It is because the sun is hitting the equator directly. We call this having a high insolation. Whereas at the poles, where the sun, the radiation of the sun hits a much greater area, we call this having a low insolation. And I've got a diagram here for you as well. So you can see at the equator, the radiation is much more concentrated as it hits a greater area there towards the poles. What are the names of the three convection cells? If I show you this diagram here then, moving on to atmospheric circulation, we have three cells. The cell closest to the equator is what we call the Hadley cell. The cell in the middle is called the Ferrel cell. I spelt that wrong, I think. And finally, we have then the polar cell at the north. Now, what I want you to imagine is we know the equator is being hit by the largest concentration of sun. That, therefore, is warming the air. So the air must be rising here. We know warm air rises. We've learnt that in science. So as the warm air rises here, it's going round, and then it's coming back down there. So we know now that the air is coming down here as so. Now, I tell my classes, I like to imagine now swimming lanes when you go to the swimming baths. If we imagine that, we can get all this correct. If it's going down here, it also must be going down there as so. So we know the air is falling in these two areas. It's falling there, you follow it round, therefore it must be rising there. It's rising here, and therefore the swimming lane scenario, it is rising there as well. Before also, you follow it round, and it is falling there. As long as you can remember that it is rising at the equator, you should be able to fill the rest of that in yourself without even thinking, just by filling in the gaps. If this is 0 degrees latitude, this is 30 degrees north, this is 60 degrees north, and finally, the North Pole, this would be 90 degrees north. And note, this is all happening on the other side of the Earth as well, but we're at the minute just looking at the north. The next thing you need to be aware of with this is high and low pressure. Now, this confuses a lot of people, so what I want you to do is I want you to imagine this scenario. Imagine that you were stood on the floor and a book fell on your head. Would you be experiencing high or low pressure with something falling down on your head? I'll say that again, there's key words in there. Would you be experiencing high pressure or low pressure if something was falling down on your head? You'd be experiencing high pressure. So let's go back to our diagram. If we are experiencing high pressure when it falls, this must mean there is high pressure here where the air is falling. Now you can identify pressure. Now you can identify here as well, the air's falling here, so this is also high pressure, HP, not for Harry Potter, high pressure. And the opposite must be happening then where it is rising. So here must be low pressure. Low pressure there and low pressure here. So we have low, high, low, high. Now, as air rises, we know when it gets really, really high up, it likes to cool down. Now, I'll change my colour here to grey so we can, I don't have grey, so we'll go black. As the air rises, it cools and condenses into clouds. So here we have lots of clouds. We also must have clouds here then, because the air's rising there. And clouds means rain, so we get lots of rain where there is low pressure. And we get lots of rain where there's low pressure here. Now, the only difference is this place is going to be very, very warm. This place isn't going to be as warm. Your example of a country sitting along the equator is Brazil, the Amazon rainforest. And this one is us, the UK, where it's nice and wet most of the time, but much cooler than Brazil. Your other examples then, the other place is going to be nice and sunny and dry. Could say this is Egypt, and at the North Pole as well it's going to be nice and sunny and dry. The only difference is it's going to be cold. Something to pick out there is what lots of people, the Arctic. What lots of people say here is go, oh yeah, but sir, the Arctic's wet, isn't it? Well, no, it's not. It's frozen solid ice. It's actually a desert. Both of these two places are deserts. Desert just means lack of water. Egypt's got a desert around it, as does the Arctic. This is just frozen. Skip back that, we've done that bit. Elements required for the formation of a tropical storm. Go on, have a think. What do you need for a tropical storm to form? Yes, you do. You need water to be at least 27 degrees, and it needs to be an area of low pressure. Without these two things, you are not going to get a tropical storm. Let's go through it. If this was the sea here, let's imagine that the sea is 27 degrees, like I've said, and the conditions happen to be low pressure. What happens now is the sea warms the air above it. We know warm air likes to rise, so that's going to rise up as so. And like we said before, as air rises, it likes to cool and condense into clouds. So we're going to get lots of rain as well, but I'm not going to draw that in because it'll get too messy. Some of you will be saying, but sir, it doesn't rise up. No, it doesn't just rise up perfectly. Due to the Coriolis effect, keyword, Coriolis effect, that air doesn't just rise directly up. It actually rotates round due to the rotation of the Earth. Now, as that happens, the air reaches the top where it cools down, and because it's cooling down, you get high pressure at the top. And what this high pressure does, it does one of two things. Some of it comes down the sides of the hurricane, and it gets sucked back in, and the process continues. That happens on both sides. Some of it, though, falls back down the centre of the hurricane. Ah, that's the eye, correct. This is the eye of the storm. Now, because air is falling down, you have areas of high pressure in the eye. So if I just make a note down here, in the eye, it is high pressure, it is calm, and it is dry. Whereas here, it's going to be very, very windy, very, very heavy rain. And that is the formation of a hurricane. And I've got a diagram for you here as well. You can see, eye of the storm, air rises, it's rotating as it does. That's coming around the edges, back down and being sucked back in from an area of high pressure to an area of low pressure. And again, the eye of the storm, the air's falling down the centre where it's calm, dry. And that's that, I think. Warm seas are 27 degrees. Excuse me. Warm air rises, Coriolis effect spins it. The warm air condenses into clouds and it rains very, very heavily. The cold air sinks into the eye here. Tropical storm directed by external trade winds. So it can be directed due to winds on the outside of it, just pushing it either one way or another. That's why they can be unpredictable. And tropical storms lose energy as they move over land or over colder water. That question came up last year. It was just a single mark, I think, from memory. An example of a tropical storm you've learnt about was Typhoon Haiyan, which happened in the Philippines. What we have here is a map of the route on which this tropical storm was predicted to travel. It went over the South China Sea here, and this is called, you think, well, so did it just get bigger and bigger? Well, no. This is called the cone of uncertainty. As forecasters, they do not know the exact path that this hurricane might travel. They can predict, however, that it will be going in this direction, and it could go either slightly left, slightly right, up or down, and this is called the cone of uncertainty. If you do get a map as such like this, just be aware of these dates so you can work out which direction it's moving. Last year we noticed that a few students, what they did is they described the movement of it actually going this way, which would be incorrect if you just simply look at the dates. Managing tropical storms then, they are going to happen. Tropical storms will always happen. What we can do though, is we can manage them and attempt to reduce that risk. What can we do? The first thing, satellite imagery. Look at that, how beautiful is that? You can see the eye of the storm there. If we can use satellites to monitor it, we can tell what direction that storm's going, therefore we can prepare for it coming, tell people about it. These are called hurricane hunters. What they do is they fly into the hurricane, they're specially adapted planes. They collect lots of data to do with pressure, to do with wind speed, and they send that back to Earth to give people the heads up. Heads up, guys, there's a tropical storm coming. This is it's called a cyclone shelter or a storm shelter or hurricane shelter, however you want to call it. The most important thing, you'll find them more or less in LICs as opposed to HICs. They are made of concrete. Yes, that's correct. They're made of concrete to withstand strong winds. You can see they are raised off the floor, so in case flooding occurs, people will be safe. And they're fairly big, so they could fit maybe a small village in there, and you'll find these dotted around some LICs. Reinforcing windows. You can see this gent here in America is placing a metal corrugated iron card to protect his windows from shattering. Educating people, telling them how to be hurricane ready. Again, an earthquake, hurricane survival kit, and finally an evacuation route. These are all things we can do to manage a tropical storm, to reduce the effects. Like I said, we know they are going to happen, but it's about reducing those effects. Why does the UK experience extreme weather? You need to know a UK extreme weather event, which I'm going to go through with you shortly. But to begin with, this is a map of the UK. And we can see that we're at sort of what we call a roundabout. Now, the UK is experiencing the polar continental air mass every once in a while from Europe. We've got the Arctic air mass, which can get very, very cold weather, as the polar maritime air mass. We have all these different air masses attacking us at different times of the year, which explains this. This was me. This was the beast. What's it called? The beast from the east. Beast from the east. That happened just over a year ago, wasn't it, when we had those 4 snow days that were cracking. We had the beast from the east in one year. That was when a polar continental air mass came into the UK and we had lots of snow. But then in the same year, we had this. We had one of the hottest heat waves we've ever had, and it broke, records time and time again. That was when tropical continental air mass came in, bringing us that nice hot weather. And it was all to do with this, the atmospheric circulation model, which I showed you previously. We know the UK here lies at 60 degrees north. We happen to be between the ferrocell cell and the polar cell. Now, if we're getting the polar cell air like that, the cold air is coming across the UK. But sometimes we get the ferrocell cell, which if this is slightly warmer air coming from the south, we can also get the warm air. What you have up here is called a jet stream. The jet stream is a band of air which... I'll start again. The jet stream is a belt of air which travels around the Earth at around 60 degrees north all the way around. However, this belt of Earth can sometimes go south. Now, if it goes south, that means the polar cell will now extend this far. And that will bring much, much colder weather to all of these areas here. Likewise, let me get rid of that, redraw it. Likewise, this jet stream, which is normally about here, can move north. This is what happened in the summer. As the jet stream moves north, that means we experience more of the ferrocell cell, bringing that warm air to the UK, which we experienced in the summer. That can be quite complicated, so any questions you've got, fire them Miss Morris's way now. Your example of UK extreme weather event is this. It was this Somerset level floods, I believe in 2014. Now, Somerset level floods, if you're unsure where it is, you can see down here, it's in the southwest of the UK, next to the Bristol Channel. And one thing I want to tell you is, it is next to the Bristol Channel. It is right next to this big body of water. And it also has numerous rivers flowing through it. So your example is the Somerset level floods 2014, not Boss Castle. I will come to Boss Castle later on in this presentation. What were the causes of the Somerset level floods? On the board here, I have put up an OS map for you. Now, we went through this a few weeks ago in class. We can see that here we've got these orangey brown lines. These are contour lines. These show you the height on land, and we know that the closer they are together, the steeper the land. For example, if the lines are like this to get close together, we know the land would be quite steep like that. Every line represents 10 metres. If the lines are much further apart though, the hill is much more gradual, and if there's no lines at all, we can presume that it's flat. Now, if you look around here, there are hardly any brown lines, suggesting this area is completely flat, which makes sense because it's got a river going through. What happened was, if we go back to this picture here, there was an area of low pressure over the Bristol Channel, meaning that some of that water came back up the river. As that water came back up the river, here, it came back up the river, it flooded either side. There'd also been a lot of heavy rain around that period of time, so a lot of this ground was already saturated. You put two and two together, you've got low pressure, saturated ground, which is also flat, and you've got a disaster waiting to happen. That caused the flood. So what were the impacts? Lots of you might think, oh gosh, I can't even remember what any of the impacts are. But you've done this time and time again, so let's just imagine it for a second. Let's look at this map again. You have an urban area here with lots of waterways going through, which flooded. You tell me. Certainly, people are going to be made homeless due to their flooding houses. Businesses are going to be put out of business due to the shops being flooded. There's lots of vacant land here, suggesting this is farmland. Farmland crops were destroyed. That might have increased food prices. I'm developing my ideas here, ladies and gents. This is what we'd expect you to do in the exam. Let's go through a few more. Longer journey times, local road closures, 600 homes affected. Some villages were cut off. Farmers were prevented from grazing their animals. Many cows had to be evacuated or sold. Major roads blocked. Local businesses lost trade. There were reports of increased crime. Instead of saying that, you could also include the word looting. Looting is when people steal when something's been abandoned. And some homeowners were forced to evacuate out of their property. My advice to you on that would simply be, just remember a couple. 600 homes affected. That'll really excite the examiner, thinking that you know your stuff very, very well. You might say this one, where's the cows one? Yeah, farmers prevented from grazing their animals, so lack of income there as well. How do they respond to it? Two simple things. First of all, they installed these giant pumps. What they're doing here is there's flood water on this side of the picture, which you can't quite see. They're pumping that water back into the rivers after the flood subsided, and they also then dredge the rivers to increase their capacity. Dredging, ladies and gents, if we look at the cross-section of a river here, what they do is they put a JCB. I'm not going to attempt to draw a JCB, I'm not very good. But if a JCB, a big digger, and they dig out some of this ground here. So therefore, once it's done, the river is much deeper and therefore can hold even more water, so it's less likely to flood. Climate change. I'm going to have a quick drink and then I'll be with you. Climate change, ladies and gents. Now, just getting mic'd up again. With climate change, well, me and Miss Morris had a discussion. Nothing came up on climate change last year. What evidence exists for climate change? How do we know it's happening? It's always in the news, but how do we know it actually exists from time and time and time again? First thing, these are called ice cores. What they do is they go to places like Arctic and Antarctic, and if this is the surface of the Earth, they drill down here and take out a core of ice, Exhibit A. Then what they do is they slice some of this out, and they take some of the gas samples in that ice. With their science equipment, then they can test that to see how much carbon is in it, and that determines what the temperature of the Earth was a very, very long time ago. The next one is tree rings. Tree rings, what we do is we know that every ring represents 1 year. Some people will question that, but just let's take our word for it. Each ring represents 1 year. The further apart the rings, the more growth that year. So for example, this one which I'm drawing now, you can see, this is a very, very exaggerated example, but these years here, 1, 2, 3, 4, 5, 6, you can see these 6 years, they are very, very close together, suggesting not much growth, suggesting that the temperature wasn't very warm. All of a sudden, the distance in the tree rings has increased. Therefore, these years, it must have been much warmer and the tree grew much more. Finally, glacial retreat. Excuse me, I can't stop hiccuping. Glacial retreat. We know that the glaciers, simply from photographs, have retreated over the past decades. That is evidence of climate change. So what does the evidence tell us? What we can do is we can establish that the climate of our planet has changed over the past 400,000 years. There's just a note here as well. On the board is a figure. You are definitely going to get figures in all of your exams, exam 1, exam 2 and exam 3. Please study them. Look at what the left-hand axes say. Look at what the bottom axis says. And we can see here this is 0. This is 400,000 years. So if this is today, this is our climate 400,000 years ago. And we can see our climate was warm, cold, warm, cold, warm, cold, warm, cold. And it happens to have done that 4 times, and I'm going to come back to that shortly. It's happened 4 times. FYI, ladies and gents, humans did not exist 400,000 years ago. That's going to be a key part of your learning very, very shortly. How does climate change happen? What are the causes? How does it cause naturally, physical or natural causes? First thing, sunspots. Sunspots are very, very warm parts on the sun's surface. If a sunspot, let me change my colour so you can see that a little bit clearer. If a sunspot happens to be facing Earth, we are going to receive more radiation from that, and as a result, our temperature is going to go up. Now, this doesn't just happen, oh, today we were facing a sunspot. This happens over thousands and thousands of years, and we will be facing it for a while. The next one is volcanic eruptions. Hopefully some of you know that the gas that comes out of it is sulfur dioxide. What that does is that mixes with water in our atmosphere. Then very, very high up, you get this water and sulfur dioxide mixing, which acts as tiny little mirrors. So when the radiation comes in, it is sent back out, it reflects back out, and that reduces the climate. Finally, the last one, and the most important one in my opinion, is orbital changes. What we have here, ladies and gents, is if you imagine, I'll do an example here, if you imagine that this is the sun, our Earth rotates around the sun once a year, pretty much in a perfect spherical shape. However, every 100,000 years, this changes, and it changes to be what we call elliptical. You can see it's a bit more oval-like there. Now, normally, the Earth is the same distance from the sun, but when it goes more elliptical, and I have exaggerated that, it won't be that extreme, when it's far away from it, it's going to receive less radiation, and it will be cooler, whereas here, it's much closer to it, and it will receive more. That then changes the Earth's climate. And if we go back to this, have a look at that. That happens every 100,000 years, and this has happened every, this goes back 400,000 years. 1, 2, 3, 4. I will be coming to that again. Human causes. First one, deforestation. If we chop down trees, from science, we know that is going to stop photosynthesis happening. We know that fossil fuels are causing global warming. We get that from transport, so cars, and things like factories. And finally, the third cause is agriculture, And someone will say, but sir, cows existed naturally? Yes, cows do exist naturally, and they do produce methane naturally. However, due to the human population, if I make that note there, due to the human population increasing, we have bred more cows that are producing more methane, therefore there are more greenhouse gases. So I'm going to go over with you the greenhouse versus the enhanced greenhouse effect. Let's imagine that this is Earth. Now, all of a sudden, Earth existed, and there was trees, and there were things like cows that just naturally existed. As well as naturally existing, in our atmosphere was the gas oxygen. Oxygen just naturally started floating around our atmosphere, as did the gas CO2. It just naturally started floating around our atmosphere, as did methane. Let's do purple for methane. I don't know the thing for methane, so I'm just going to do an M. This, remember, ladies and gents, is before humans existed. Radiation comes in from the sun. It is reflected back, and some of it is absorbed by things such as CO2 and methane. Some of it comes in and reflects straight back out, but some of it is absorbed by that. We call this the greenhouse effect. Without this entire process happening, life, like the cows and the trees, would not exist on Earth. Earth would be a big ball of ice. So the greenhouse gases, like CO2 and methane, are pretty important for keeping our planet habitable, meaning people living. All of a sudden, us annoying humans come along, and let me get my red pen, and we breed more cows, and we decide to chop down trees. And more importantly, we even start building factories which produce all these gases. All of a sudden, what you've got is you've got loads of CO2 in the atmosphere now. You've got loads of methane in the atmosphere now. And with all these gases, you guessed it, when this radiation comes in, oh my gosh, when this radiation comes in, less is escaping and more is being absorbed by these gases. And this is heating our planet. That is the enhanced greenhouse effect which humans are inducing. Here's a diagram, just a little bit clearer than my drawing. On both of them, look, natural without humans, human enhanced greenhouse effect. Things to look at there, more heat escapes into space, less heat escapes into space. Why? Because there's more CO2 and methane due to that production which humans are doing. You may be asked the question, what's the main cause of climate change? Is it physical and natural causes or is it human causes? Well, I want you to remember this graph here, because if we go back 400,000 years ago, we know this orbital change happens every 100,000 years. Therefore, natural causes are responsible long term. But in the last 200 years, what we have seen happen, so if this was 200 years ago and this was today, we have seen our climate shoot up like this. And that's because of human-induced global warming. Therefore, in the last 200 years, humans have been more responsible. So long-term, natural, short-term, human. That could be a classic 9-mark question, that, where you'd have to explain how orbital changes do affect the climate. So you'd say the Earth can be closer to the sun, which receives more radiation, or further away to receive less. This happens every 100,000 years. This is responsible for long-term climate change. However, recently humans have started producing fossil fuels through transport that burns more CO2 into the atmosphere. That's occurred over the last 200 years, which has resulted in the enhanced greenhouse effect and our temperature rising much more rapidly. What are the effects of climate change? You can work them out. First of all, drought. It's going to get very, very warm. You're going to get lots of drought, water shortages. This is sea level rise, depicted by the red. These areas are influenced by sea level rise. This is unreliable crop yields, meaning we don't know really the impact it's going to have on our crops. Some may grow more, some may grow less. Overheating, so it's going to have an impact on our health. That might put pressure on healthcare systems. Some of you will be saying it puts pressure on the NHS. Yes, it does, but specifically if we're talking about the globe, everywhere doesn't have the NHS, so you can just say healthcare systems. Very few people discuss the positives of global warming. Now, I'm not saying there's loads, but certainly, I tell you one thing, heating bills will be reduced. That's a great thing. And also, in winter, there will be fewer deaths of the elderly. Happy days. However, there could be more in the summer. So when it says about effects of climate change, don't necessarily think it's always talking about the bad things. There are a few good things which you can pull out. And again, you are developing your answers, so don't just say sea level rise. Make sure you can say that impacts on flooding, farmers' crops. You might say it impacts on people's homes. That's a financial cost, or shops, therefore can't sell produce. How can we manage it then? Two main things. This is the last bit on climate change. First thing, mitigation. This is about preventing and reducing the amount of greenhouse gases. How can we prevent or reduce the amount of greenhouse gases? First one, renewable energy. Solar panels, wind farms, these are creating electricity without producing greenhouse gases. Afforestation, planting trees, it's going to increase that process of photosynthesis. Carbon capture, literally grabbing that CO2 and pumping it underneath the ground. However, the risk is if it escapes, could be chaos. And finally, international agreements. The most recent international agreement, which we've learnt about, was on the pre-release. It is the Paris Agreement in 2015. That is the latest time all the leaders of the world came together and decided, let's all reduce our CO2 emissions. Unfortunately, Mr. Trump has now got involved and decided to pull America out of that agreement, which is very, very bad because America, per person, is the largest producer of greenhouse gases in the world. China is the largest, but per person, it's America. USA, sorry. What was I going to say on that? Sorry. International agreements are super important because imagine us as the UK. If we produced all of our energy from renewable, we planted loads of trees and we captured all our carbon in the UK, that's awesome. We're carbon neutral. But unless everybody does it, we all share the same atmosphere, it's going to spread around the world. We can adapt, we can manage our water supply, desalination. If this is the sea here, this is the sea and this is the land, what we can do is we can build a factory. We can pump that seawater in, we can filter it and put fresh water out. Because if there's going to be less water, we're going to need something to drink. However, that's really bad because that produces CO2 as well. So that's really expensive and it kind of does the, not controversial, what's the word? It's a bit of a hypocritical method. You know what I mean? It doesn't counteract climate change, it actually enhances it. Changes to agriculture systems. If you live in an area where a specific crop grows, but then due to climate change that crop no longer grows, change that crop. Find a crop which does grow in that area. For example, in hundreds of thousands of years' time, we may end up growing bananas in this country if our climate suits it. However, it's limited because eventually everywhere will be so dry that you won't be able to grow anything. And finally, reducing the risk of sea level rise, that Thames barrier. If sea levels are going to rise, let's put some barriers in defence, so make sure it's not going to flood. And a classic question, what is the best way to manage climate change? Please don't say either. Please don't just say it's just adaptation or just mitigation, unless the question specifies so. It's a combination of both. Mitigation is important to reduce levels of greenhouse gases for the future. Greenhouse gases for the future. That is super, super important for the future. However, adaptation, we're going to have to do it, ladies and gents. Sea levels are rising. This is to prevent current climate change. We can already see the effects happening. We have to adapt now, otherwise we're all going to die. But we can also limit it in the future. Please don't just say that in your exam. Ecosystems. I'm gonna crack straight on. I'm just grabbing my bottle. We've got a record-breaking 12 viewers at the minute. 17 was the record, I've just been told. We've peaked at 17 at one point. Right, FYI, how long have we got left? We probably have like 3/4 of an hour left, maybe half an hour. Ecosystems. To begin with, what have we got here? Biotic and abiotic features. In an ecosystem, you've got things which are living and non-living. The things which are living we call biotic features. They are things like insects, animals, plants, or a fungus, can even be grass. We also have abiotic features, which are non-living things, air, climate, water. And these things are constantly interacting with each other. For example, insects, animals, plants, they all need air, don't they? Plants need the sunlight to be able to grow. So biotic and abiotic features are constantly interacting with each other. You need to know about food chains. Food chains are very, very important and they're also quite cool. Producers are things that make their food from the sun, photosynthesis, like a plant or grass. Consumers, like the grasshopper, eat the grass. A secondary consumer would eat the primary consumer. So if the grasshopper was the primary consumer, in this example, the bird would be the secondary consumer. You could argue then that the snake would be the tertiary consumer as well. Or that could be the the third consumer, and the owl could be the tertiary consumer. But more important, you need to know this. This is what we call nutrient cycling. Nutrient cycling is when all of these animals, once they have died, the owl, for example, the owl will fall to the floor, in theory, if it's not eaten, and once it's decomposing, those nutrients will go back into the ground, which will feed the plants, and it's the circle of life. Happy days. You need to know an example of a UK ecosystem. We taught you about Epping Forest, that is northeast of London. Here it is. A few facts about Epping Forest for you. Remember, this is your example of a small-scale UK ecosystem. Most of the trees are deciduous. Deciduous means it loses its leaves in the winter. They grow broad green leaves, so their leaves aren't small, they're huge like this. Nice big leaves to maximise photosynthesis during the summers, because think, if you lose your leaves in the winter, you want to maximise that sunlight intake during the summer. They shed their leaves in the autumn, and so to conserve their energy during the winter months. Tropical rainforest, that is a cracking gift there. We have a jaguar on the grand piano playing a few tunes. Location of them to begin with. We can see on this map they are in the dark green area. This is the equator. Remember the equator, this all links together, isn't that fantastic? The equator has a high insolation, that is insolation. Has a high insolation, meaning that it's experienced a large concentration of sun. We know here there is low pressure, so the air is rising. That cools and condenses, so the air is cooling and condensing all in this area here. That creates rain, which creates the perfect growing conditions, which is why tropical rainforests are found here. It's hot and rainy, perfect growing conditions for tropical rainforests. There we go, got the Hadley still on there for you as well. So this is where tropical rainforests are found, down here. As the air rises, clouds form, very rainy, very warm. You've got different layers of the rainforest. The first one is the forest floor. Down here, you have large buttress roots. Spell buttress for me. Buttress roots, like that. They are very large to support the 30-metre tall trees which can be there. Understory layer can be still very dark down here. So, what was I going to say about that? Dark, I can't quite remember. But it's very dark down there. Oh, they've got large leaves here as well. Very large leaves to absorb any sunlight which can break through. The canopy layer, you can see the canopy layer, things are starting to grow a little bit higher, but the emergent layer in particular, this can be up to 50 metres tall, and they are competing for, you guessed it, sunlight. Animals in the rainforest. This is a sloth, or if you are David Attenborough, he calls it a sloth. And adaptations of the sloth or the sloth, it has very sharp claws which are curved to grip onto that. You can see that its colour, its fur is for camouflage. And finally, it moves very slow to avoid predators. You also have this. This is the harpy eagle. This goes through the rainforest and it has a short wingspan to avoid bashing into all of those trees. They're trees, by the way. It also has very good eyesight, so it can see its prey from far distances. Your example of a tropical rainforest, look how beautiful that is. It is Malaysia. And you need to know causes of deforestation. Why on earth would we chop down all of these trees? First of all, logging. Logging is to make things like furniture. They will sell that wood for all sorts of bits and pieces. Farming, if the population is increasing, we need more space to farm. And finally, housing again, so pressure of space to build. Effects of deforestation. Well, look at that straight away. We know there's going to be a lack of CO2 in our atmosphere, but let's see what else we got. Soil erosion. This soil is going to blow away if there's no trees, so you won't be able to regrow them. Water then can become contaminated, which is really bad for local indigenous tribes, because they will become ill. Loss of plants for medicinal purposes. Some of you will remember this from going through paper 3 stuff the other week. We know that there is lots of cancer reducing drugs that come from the rainforest, and we're chopping it down, and finally increasing CO2. But don't just say increasing CO2. That then is going to make ice caps melt. That is then going to increase sea level rise. That is then going to make people homeless, reduce income, all that sort of business, which you can develop your answer. How can we manage it then? How can we stop it? Oh, sorry, there's a couple more there of deforestation I forgot. You've got the positive effects as well. It does create jobs as woodcutters. That is going to generate an income. It is going to income from profit. So if people are having farms there, they are going to generate an income from there. It's very similar to the climate change one. There's not necessarily always bad things. How can we manage it? Selective logging. This is selecting older trees to chop down. Older trees, not the new ones. Select older trees to allow the new ones to grow. International hardwood agreements, so people coming together internationally and agreeing of specific trees not to chop down, to make illegal, not to chop, otherwise they may be going extinct. And finally, ecotourism, so this is reducing the impact. People will pay locals to stay in maybe huts / learn their lifestyle, and all income will go back to ecotourism as opposed to like British Airways or Thomson. Cold environments. There's a polar bear there. Example of a cold environment, you've learnt about Svalbard, which is part of Norway. It is a Norwegian island, very similar to how Northern Ireland is part of the UK. It is not on the mainland, don't mess it up. Svalbard is an island part of Norway. Characteristics of Svalbard, well, the temperatures are very low, hence cold environment. The soil is near enough permanently frozen. The polar bears are adapted in a number of different ways. White fur for camouflage. They have a layer of fat to keep them warm. They have a large pores so they don't sink into the snow. How are plants adapted? Well, if it is very cold, they don't want to lose water, which then freezes, meaning the plants have very waxy leaves, therefore reducing water loss. But why on earth would you want to live here where it's very, very cold? First reason, mineral extraction. There is things like coal and copper there, which people can drill for. They can earn an income by being that mineral extractor and sell that on for money. Fishing. They have some of the richest waters in the world. They can then fish for that water. They can fish for the fish. They can sell the fish. They can eat the fish. Tourism, very, very popular place for whale watching. With this, if you're going to say an opportunity is tourism, please don't just say whale watching. Say therefore people can earn an income from it. Therefore they can pay tax to the government, and that is then going to improve their education and healthcare. We all know though, ladies and gents, it is very, very cold. Therefore, what are the challenges? Why is this all difficult to happen? First thing, it's very cold, extreme temperatures, meaning things like mineral extraction being out in the cold is difficult. Construction is difficult. The land is permanently frozen, making it difficult to build things like this, hence it being on stilts. Infrastructure. If you want to build a house, imagine trying to lay a pipe down, a water pipe. That water is going to freeze, meaning it has to be well insulated, meaning it costs more money. Infrastructure is very difficult. And finally, accessibility. If we're talking about fishing and tourism, fishing will be limited because of the frozen water. Tourists will find it difficult to get there in winter months via boat because of that frozen water. So they would have to fly in, which again is quite difficult. What threats to the cold environments do we have? First of all, global warming. As it warms up, ice is melting, therefore sea levels are rising, and that is threatening the habitats which live there. We've all seen those pictures of the polar bears before, which are very, very thin, and they don't have any food. But we can manage it, ladies and gents. There's 3 ways that we can manage it. First of all, technology. We can still access the oil there without impacting on the ground. for example, let's say over here is where the drill for the oil is. They have now pumped this oil through this pipeline, which is absolutely fine because this pipeline, first of all, one, is well insulated. If it's well insulated, that means it's not going to melt that permafrost. Number two, it's on stilts, meaning that animals can roam freely underneath it. That's not going to affect migration patterns. Number three, it is on suspension points, meaning that if there's an earthquake, it won't break. You also have international agreements, work from the government and conservation groups like WWF, not the Wrestling Federation, but World Wildlife Fund. They protect and educate, they educate people who live in the area and protect the animals that live in the area from going extinct. Coasts, quick drink. Starting with coasts, you can see the GIF there. I'm going to go through it all. Coasts and rivers are one of the smaller options, but coastal erosion. This is a picture of the Holderness coastline. We can see there used to be a road that used to go along the Holderness coast, but unfortunately it started to erode. This is soft rock boulder clay. To begin with, there are three processes of erosion that you need to know. When the sea comes up here, it will attack the cliffs. It will force air and water into a crack, breaking pieces of rock off, like I'm drawing on the board now. The next bit, when the waves come up, they are holding these large rocks. Those rocks will be thrown at the cliff face in what we call a sandpapering action. That is going to erode the cliff even more. And finally, sometimes these rocks are going to collide with each other. That's attrition, and they'll become rounder and smoother. Landforms of erosion then. Key terminology here. I don't think they'd ever ask you. I mean, it'd be very strange if they asked you to explain the formation of a waterfall or cave arch stack stump. They're probably going to use this terminology, landforms of erosion, meaning that you need to identify the landforms of erosion. One of them is headlands and bays. First of all, if you swam along this coastline, we can see that it goes hard, soft, hard, soft, hard, soft. This is called a discordant coastline, where the bands of rock are different. If you swim along this coastline, it's a hard rock all the way along. This is called a concordant coastline. I'm saying it, concordant. Way to remember it, discordant, different, concordant, consistent. Discordant, different, concordant, consistent. Now, if a massive wave attacked this, what's going to happen? Yes, you're right. It's going to go hard. It's going to stick out. The soft is going to go in. This is where you would get a bay. This is where you would get a headland. And now that the bay is sheltered, you would get constructive waves here, building up a beach, whereas the destructive waves would be attacking the headland there. Wave cut platform, next one. This would happen most likely at a concordant coastline, and it would be on hard rock. Hard rock such as limestone or chalk. Someone said to me not too long ago, said, but sir, chalk isn't really a hard rock. I've seen teachers use chalk before and you can snap it in your hands. Yes, you can. But imagine this. If you had a ball of chalk in your hand and a ball of clay in your hand and you squeezed them both, the clay would change shape, the chalk wouldn't. So in terms of rocks, we're classifying it as a hard rock. You've got a cliff here, you've got the sea. What happens is the sea is constantly attacking through hydraulic action. That hydraulic action creates this wave-cut notch. That leaves the land above it unsupported, and due to that force gravity eventually pulls that down, leaving a wave-cut platform. This process retreats as the wave-cut platform moves back. Landforms of erosion, this time a cave arch stack stump. I'm going to draw this one out because I find it easier than showing you a diagram. Just to show you where this comes from, if we go back to this part here, let's clean that. Sometimes the waves are attacking head on there. Sometimes they attack on the side. Right now, I am showing you when they attack on the side, okay? So if we imagine that headland is sticking out as so. Sometimes you just happen to get a crack in the side of a headland or a line of weakness. It just happens. You get a crack / line of weakness. Hydraulic action attacks that crack. Water and air get forced into that crack and then it becomes a cave. Now this cave then becomes deeper because abrasion attacks that cave, widening it and deepening it further back. Eventually that cave then becomes so deep, and bearing in mind it's happening on the other side, you get what you call an arch like that. Now this is the cave that's fully broken through to the side now, and we can see the water. What happens now is at the base, bearing in mind the water line is here, abrasion and hydraulic action still attack the bases of the arch. This then is going to become weakened here and here, meaning that the land above it again is going to become unsupported, and due to gravity it eventually collapses, leaving a stack. That stack, you could say, is further eroded from the base and eventually falls over to become a stump left over. The key thing with that, ladies and gents, is just using your process of erosion at the correct time. Crack, eroded by hydraulic action. Abrasion deepens the cave. Eventually it breaks through to the side. Weakening from the base from abrasion and hydraulic action. The top of the arch becomes unsupported and collapses, leaving a stack. That falls over to become a stump. Bit of a clearer diagram here. Crack, cave, arch, stack, stump. If you want to pause the video here and quickly go over it. Methods of transportation. Oh, I love longshore drift. If this is the shoreline here, this is the land, this is the sea. We're now talking about that eroded material. We are talking about now that eroded material that's been taken off the cliff. Well, let's start here. Let's just focus on one tiny piece of sediment. There happens to be a prevailing wind here. This is the direction of which the wind is travelling. That wind is going to blow this sediment up the beach. When the wave goes up the beach, we call it the swash. Gravity pulls it back down. You guessed it. That's the backwash, sir. Yes, it is. This is the backwash, which gets pulled down by gravity. But ladies and gents, this process doesn't just happen once. It happens again and again and again. This process continues all the way along the beach. Swash, backwash, swash, backwash, swash, backwash, swash, backwash. The only things I've missed off here is the swash moves up the beach at a 45-degree angle. The backwash moves down the beach at a 90-degree. 45-90, 45-90, swash, backwash, swash, backwash. Diagram for you, exact same again. You got the prevailing wind, swash, backwash, swash, backwash, swash, backwash, swash. And longshore drift, or LSD as it might be abbreviated, moves in this direction. Then we have the formation of a spit. Let me just set this up. If you are asked to explain a feature of a landform of deposition in coasts, you could talk about the formation of a spit. The first thing you need to do on here, which everybody makes this mistake, is at this point nobody talks about longshore drift, and it's where you can pick up easy marks. A spit begins by longshore drift going along a beach. It moves up at a 45-degree angle, back down at a 90-degree angle. It's called the swash, the backwash, the swash, the backwash. Talk through what we've just done, including that key term there, the prevailing wind. Eventually, though, we get to the end of the beach, and longshore drift doesn't just stop. Have I drawn that right? Yeah. Longshore drift doesn't just stop. It continues. But we've got to a river estuary where there's a river meeting the beach. We know that the river is flowing this way towards the sea. We know that the waves are pushing this way towards the river. So what happens? the material gets deposited, that sand, the material gets deposited at the end of the beach as so. And this is the formation of a spit. Longshore drift then continues along the spit, forming it. But what sometimes happens then is you get a secondary prevailing wind. And what that does is that causes the spit to slowly curve, giving it a recurved end. The water from the river can still escape, but the spit has now curved around. Because this water then becomes kind of what we call stagnant, very still behind it, you get salt marshes forming and mud flats behind the spit. Sometimes spits can become so big that you can actually build on them as well. A diagram of a spit there, longshore drift occurring along a beach. It sticks out then into the river estuary. Fun fact, well, it's not a fun fact, it's just a fact. If the spit continues moving over, it can create a beach bar. That wouldn't happen across a river, it would just happen across a bay. That's a beach bar if the spit moved to the extended right to the other side. Again, if you're unsure, pause that and have a good look at that yourself. Coastal hard engineering. We know the coast is eroding. Different forms of hard engineering you need to know. First of all, this is what we call a groin. A groin extends into the sea at a 45-degree angle to prevent longshore drift. These are called gabions. They are rocks in metal mesh cages placed at the base of a cliff. This is a sea wall. A sea wall is at a cliff face. It's quite often recurved like this to reflect the energy. And finally, riprap as well. Riprap or rock armour. I am going to go through these once more. First of all, the groin. The groin extends into the beach. It's made of wood or rock at a 90-degree angle. We can see on this photo here, there's lots of material on this side and there's not a lot of material on this side. That's because longshore drift must be occurring in this direction. So the groin has prevented that. Therefore, when the waves attack the beach, the waves are eroding the waves are being absorbed by the beach as opposed to the beach not being here and it being absorbed by the coastline and eroding. Good things about a groin, they're not too expensive. They're about £2,000, I think, per groin. But the bad thing is they can reduce access to the beach. People can cut themselves walking over it, and they do, let's be honest, they do look pretty ugly. Gabions, they're placed. These are really, really cheap form of hard engineering. You can do them yourself. So a few people on the coastline have done a DIY version in front of their homes. They can be easily damaged though. And if they're easily damaged, those rocks can come out onto the beach and cause cuts on people's feet. The sea wall, very, very effective. The waves come in and it reflects the wave energy back. This reflects the wave energy. The riprap absorbs wave energy. The riprap or rock armour absorbs waves energy, that should say wave, reducing coastal erosion. You also have soft engineering. You've got plenty of examples of soft engineering. I'm picking out two for you. This is called beach reprofiling. This is called beach nourishment or beach regeneration. Beach reprofiling is moving the sand smoothly across the beach so it's evenly spread. Therefore, when the waves attack, the whole beach can absorb the waves and the houses behind it are protected. You can see here that they've done two. They've got a sea wall and they've got beach reprofiling in front of it. Beach nourishment is replacing lost sand onto the beach, again building up the beach. Quite often these two work in unison. Good things about soft engineering. So if we quickly go, the positives of soft engineering. It's cheaper. It's attractive. So it attracts people to the beach. You spend money, tourists, tax, education. And it's cheaper, attracts tourists, it creates habitats. Bad things about bad things about it, it needs constantly doing, so you're going to have to reprofile your beach at least every year. It is less effective, bad things about it, it is less effective than hard engineering. But quite often they work in unison like this. You've got your seawall, you've got your beach reprofiling, they work side by side to make the ugly seawall not seem so ugly. Coastal management. You need to know an example of a coast which is experiencing erosion. Now, if you went back 500 years ago and drove to the coastline, you would find that you would be able to drive all the way out here to all of these villages. Unfortunately, if you go there today, where we visited, Mappleton, this is as far as the road will take you. Mappleton is right on the coastline now, and that is because this is the fastest eroding coastline in Europe. Norway is all the way over here. That is 1,000 miles. Because it's 1,000 miles, this means it has a large fetch. This is called the fetch, the distance in which the waves travel. Distance in which waves travel. Because they travel over 1,000 miles, the waves here are very, very big and very, very powerful, meaning that this coastline is eroding very, very quickly. It is made of soft rock, boulder clay. So does that mean eventually we could be eroded around here, wherever we are? Yes, yes it does. In theory, this coastline will continue to erode and erode and erode unless we do something about it. Which is why at Mappleton, we know they've put 2 groins in place and riprap. We know at Bridlington here, there's lots of riprap and different sea defences. They are installing all of these different hard engineering techniques along this coastline to prevent that erosion from happening. Happy days, everyone's going to be okay. You can still go to your amusements and Bridlington can still be a tourist destination which generates an income for the whole Ness Coast. However, I'm now going to blow this bit up to show you something negative which is happening. So if we blow this up like this, we have Mappleton here. This is Mappleton. Mappleton has about 50 properties. And remember, it has a groin there, it has a groin there, and it's got some riprap. Now, when Mappleton was chosen for the hard engineering, they thought, yeah, that makes sense. There's 50 properties there, that's quite a few people. If we continue to let this area flood, that's going to be a lot of houses falling into the sea. Now the waves come in, bearing in mind the prevailing wind comes in this direction. Now the waves come in and there's a beautiful beach that is built up at Mappleton, so it's nice and protected. So much so that even grass has started growing on the cliff. All these people are protected. However, if we just go about 3 miles south to a place called Aldborough. Aldborough has no more than about 5 or 6 properties. Now what's happened is a process called terminal groin effect. Terminal groin effect happens when the prevailing wind comes in. The waves are now intensified due to this groin being here. Why? You don't really need to know. All you need to know is, due to this groin here, 3 miles away from Aldborough, the waves coming down here now are even more intense than they were before that groin was built. Terminal groin effect. There's a farm here. There's a bloke who's got a farm with some cows. As his farm erodes, he's losing farmland. One day he woke up, and if I draw a side-on view, sorry, my pen stopped working then. His house is here, his farm. He woke up one morning and there was a cow there because some of the land had slumped down. Then they had to get a helicopter to lift the cow back up. His farmland is rapidly reducing. Essentially, all these places are going to fall into the sea. Oh, so why don't we just build more hard engineering then? There's only 5 to 6 properties. It will cost a fortune. This hard engineering here cost a fair few £1,000,000. 5 to 6 properties they don't think is worth it. So there is currently no hard engineering there. Rivers. This is the last section. What a beautiful gift that is. That's quite relaxing, that. long cross profiles then. Rivers start in the upper course. In the upper course of the river, if we're looking at the cross profile, so how do you know the difference between a cross profile and long profile? Well, look, it's a cross section. The cross profile is V-shaped. It has a very, very narrow channel and it is very, very fast flowing. It has a high velocity. The water here is moving very, very quickly. The middle channel is more U-shaped. It has a little bit of a wider channel. And finally, the lower valley is much, much flatter. The water is much deeper and it's much more slower flowing. Classic question might be just fill out this diagram. This is the long profile. Now the long profile we can see in the upper course where it's V-shaped, it is very, very steep. This gives its high velocity because the water is travelling downwards. The load size here is fairly large. Because it has that high velocity, it's got lots of energy, so it can move big boulders, rocks. We call that traction. The middle course, you can see it starts to get a little bit more shallow. The material's had time to erode down a little bit, so you've got smaller rocks here. This is called saltation, where rocks are bouncing along the riverbed, before you get suspension solution in the slower flowing water, which is much, much flatter here. This is what we call a drainage basin. A drainage basin is an area of land which is drained by a particular set of rivers. You can see this dotted line here. The dotted line represents the watershed. It's an invisible line that you can't see. What it means is, if a raindrop falls here, that raindrop will eventually make its way to one of these rivers and into the main river. If a raindrop falls there though, it will fall into this drainage basin. Other parts of a drainage basin you need to be aware of in terms of keywords: the source, where the river starts, confluence, where two rivers meet. So you can see this tributary here, a smaller river, meets the main river. That's the confluence, the main river channel, and finally the mouth or the river estuary. I've put a picture of a bath here as well. A bath is a great way to demonstrate a river drainage basin. If a water droplet fell there, it's going to somehow make its way into that plug hole. It's the same in the drainage basin. If a water droplet there, it's somehow going to make its way to that river. If you had another bath here with another plug hole, if the water droplet fell there, it would make its way into this plug hole. That's what the example there. So you get drainage basins side by side one another. Different transportation methods. Large boulders roll along the riverbed. Saltation, smaller rocks bounce along the riverbed. Suspension, small fine sediment floating in the flow of the water. And finally solution there. Even though you can see it here, this is dissolved material. You can't see it. Formation of a waterfall. Again, similar to the landforms of erosion, these are landforms in the upper course. Erosion, to begin with, hard rock sits on top of soft rock and water flows over both of them. There may be a line of weakness or a crack there, which means hydraulic action erodes that crack. Eventually, a step forms in the river. Remember, the soft rock is going to erode much quicker than the hard rock. A step forms in the river. Now you've got water moving down here and it's moving around really, really fast. You're going to get lots of hydraulic action going on in here. Water forcing its way into any crack possible. That then develops what we call a plunge pool. This is a plunge pool. You can see the water is now dropping from quite high. It's eroded a big, big hole into it. And more importantly, it's started to undercut the hard rock. Key term, it's undercut the hard rock. This hard rock is going to become unsupported. As that hard rock becomes unsupported, gravity will pull it southwards and it will collapse into this plunge pool. That's what is going to happen here. It has now become unsupported and it's going to collapse. You can see it looks like we've started fresh now, but this time you've got hydraulic action happening and abrasion. All of these rocks are dancing around in the bottom of the plunge pool here, causing lots of erosion. That's further going to undercut this hard rock and the process retreats and the waterfall moves upstream, leaving a gorge. Meanders and oxbow lakes. Middle course. We've very nearly done, ladies and gents. This is a river. All rivers start off as they are straight. If we look at the cross section of a meander, it looks like this.
there may be a little bit of weakness in the side of a riverbank. As there is a weakness in the side of a riverbank, what will happen, as the flow, bearing in mind the water's coming towards us, as the flow of water comes towards us, that hydraulic action is going to attack that crack. And what we'll see happen is it will slowly form a shape as so. We can see now that crack has been attacked and this part of the riverbank underneath the water has been eroded. This process then will become more extreme, and more extreme. So much so that material will be deposited here, creating a slip-off slope. And this part will become undercut and you will get a river cliff. Now we've got that, I'm going to draw you a meander. The water will flow the fastest on the outside, it will slingshot to the other side, and the exact same will happen here. So it's fastest flowing on the outside, it's slower flowing. Let's do a slow colour, which I know, red. It's slower flowing on the inside where deposition will occur. That is depositing of sand and sediment. So you get a nice slip-off slope here, here, and here, and you'll get a river cliff there, and there. When erosion is occurring laterally, lateral erosion, sideways erosion, so that is hydraulic action attacking here and here sideways, these two bits of meander are going to eventually become so close that they break through to the other side, and that is when the water will decide to take its shortest path, leaving this as an oxbow lake. So what you get is the water will take its shortest path as so, and you then get this oxbow lake there, which will eventually be cut off. Another diagram there for you, a bit clearer than mine. You can see the fastest current on the outside, slower current on the inside where you get sediment deposited. Features of a meander. The River Tees is your example of a river valley in the UK. It is in the north-east of the UK up there near Middlesbrough. Things to know. High Force, that is the name of the waterfall. River Tees is an example because it has a great example of different meanders, and it also has a river estuary where the land is very flat and development can happen either side. Boats will come in here, just draw a boat. Boats will come in here, deliver their produce, load back up, and off they go. Good for trade. Causes of a river flooding. About 3 or 4 slides left, ladies and gents. Physical causes. Heavy rainfall, not just rainfall, heavy rainfall. Saturated ground. If it's rained previously, the ground is already saturated. Think about a waterlogged pitch when your football game's called off because the ground is so wet you can't play. Steep valley sides. If you have, like Boscastle, if this is Boscastle here, sat in a valley, if a raindrop falls there, it's going to run straight down the valley sides into the town. That is a natural cause. And impermeable surfaces. Remember, rock can be impermeable naturally. Human causes, deforestation, chopping down trees. Trees normally absorb rainwater or intercept it. Without the trees, that ain't going to happen. And building urban areas. Building urban areas like Boscastle, you can see in this photograph here, is going to, there's going to be concrete on the floor, there's going to be tarmac. That is going to reduce water being absorbed, and therefore it's going to sit on the surface and cause that. Also at Boscastle, it happened to sit on a confluence of the Valency and the Jordan. Remember, confluence where 2 rivers meet, so there was an excess amount of water that day. A flood hydrograph. Features of a flood hydrograph. You have time along the bottom. This is 12 midday one day. This is 12 midday the next day. Up the side, you have runoff, discharge, so that's the volume of water in the river, and you have rainfall here. So, for example, what have we got? 1, 2, 3, 4, 5, 6. At just before 2 a.m. or 2 p.m, the rain started. It then got heavier before the rainfall was at its heaviest here. The rainfall then declined and stopped. Slowly but surely, this purple line then discharge. This is the volume of water in a river. The discharge slowly began to increase. And some people say, well, why didn't the discharge increase straight away? When it rains, ladies and gents, all rain doesn't just happen to fall into the river. It falls either side of it, and eventually that water makes its way to the river. That's why there's a delay. As that water reaches the river, this is called the rising limb. The rising limb increases before the river is at full capacity. Or maybe this is where the full capacity was, and this part is when the river was now flooding. This is called peak discharge, when there is most water there. Eventually, when we now know the rain has stopped, all the water is beginning to wash away, the falling limb, and the water returns to its normal flow in the river. The time between peak rainfall and peak discharge is called the lag time. A long lag time is really, really good because it gives people time to prepare. Short lag time is really, really bad. I've got two examples here. Again, you've got peak discharge here, you've got time along the bottom. Both of these rivers have experienced the exact same amount of rainfall. The only difference is this river increases quickly, this river increases slowly in discharge. This river increases quickly, we call it a peaky graph, perhaps because it is an urban area, meaning that the surface runoff is much, much quicker, whereas this one is much, much slower. This could perhaps be in a field, so water is being absorbed, so less water makes it to the river. This one's got a much greater lag time. You can see peak rainfall there, peak discharge versus, so short lag time, long lag time. You want long, so you compare. Your example of the river flood is Boscastle. Management techniques for rivers. First thing, you've got dams and reservoirs, flood relief channels, and river straightening. This dam here, you can see the dam holds back the water. You can also create hydroelectric power from that, which is superb. River straightening to make sure the water escapes the area as quick as possible. Flood relief channels. Flood relief channel might be a channel that you build underneath the ground so excess water can escape very, very quickly. All of these three, hard engineering techniques. Very expensive, very time consuming, need to be well planned. However, you can do things like soft engineering like this, floodplain zoning, which I've got on the right hand side. Afforestation, planting more trees to absorb the water. Flood warnings, get out the way, there's a flood coming, move, simply telling people. And finally, floodplain zoning. Don't build here, you can build here on stilts. You can now build a city here because you're far enough away. Simply just telling people where they can and cannot build. With Boscastle, they managed their flood by raising the car park. They also built modern bridges. Those modern bridges were superb because they weren't made of brick and stone. They were made of metal and they had slits in them so the water could pass through instead of being blocked and acting like a dam. However, people of the area weren't really happy with that because they lost their traditional bridges, which meant tourism declined slightly as well. That, ladies and gents, is the end. Tomorrow's exam includes natural hazards. It includes tectonics, atmospheric hazards and climate change. It includes ecosystems, the UK example of your Epping forest, tropical rainforests and cold environments. We learnt about their Svalbard and we learnt about Malaysia. Finally, you will be asked a question on coasts and rivers. There will be a question on glaciation, question 6, but I will tell you before the exam not to answer that question, as you won't know the answers as well as the others. Before we finish, I'm getting a notification over here that there may be a few questions, or to go to a few things.
Mr. Rams's magical sixth sense.
To show that. Ladies and gents, I'm just going to step away from the computer and load up another PowerPoint which someone's requested, if you just bear with me.
Can we see that live, Miss Morrissey? Yeah. This is a fancy bit of kit, this thing. Oh, it's blank. Ah, there we go. Menzies Magical Sixth. This is what that's the Sixth Sense film, by the way. If you haven't seen it, it's pretty scary. But I say Sixth Sense because this is stuff I think you're going to need to be 100% confident when walking into paper. Now, I'm not by any means saying this is definitely going to come up. It's just a feeling when you look through what they have tested you on. They could just test you on the same things. But anyway, let's get rid of this. Oh no, I can't get rid of that. Anyway, I will put this on Frog just before I leave school today. First of all, hazards. Earthquake key processes. If you remember that thing which I went through just before about the focus and the epicenter, they could ask you a question on that. Key process, maybe seismic waves, label this. That might be question 1A, for example. Then question 1B might be a 6 marker to do with the effects and responses. So when we talk about the effects and responses, we learnt about the HIC Italy and the LIC Nepal. If you're talking about the effects, we know that people died. Don't just say people died. Quote a figure. If you can't remember, just say roughly 300. If you can't remember Nepal, make it up. Just don't say 2 billion. A few people might be thinking, what do you mean just make it up? As long as it sounds realistic, you will be credited because you have recognised that fewer people die in the HIC and more people have died in the LIC. So I don't know, let's just go for about 6,000. We might be a couple of thousand out, we might be 10,000 out, but it doesn't matter. We've determined that the difference of the two. Similar to responses, think Italy is a HIC. They responded really well. They offered that people didn't have to pay tax for a few months. They could afford to do that because they were a HIC. Nepal, on the other hand, were donated aid, food, water because they couldn't even, get food to their people. UK extreme weather event, that was Somerset 2014. That's your example. Causes. Remember, it was low pressure, that water came in, rivers, flatland. The effects, farmers lost crops, responses, dredging of the rivers, and formation of a tropical storm. Rewind the video if you're unsure, I did go through that a couple of times. Causes and management of climate change. If something doesn't come up on climate change, we'd be very, 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 very shocked. That doesn't mean to say just spend all your time revising it, but it's just worth noting. Causes of climate change, you've got natural causes, orbital changes, sunspots, volcanic activity, human causes, afforestation, fossil fuels, deforestation, fossil fuels and agriculture. And then management, you've got mitigation and adaptation. Go back to the video if you're unsure on that. Ecosystems, threats to tropical rainforests. Adaptations of animals and plants. So we saw about the plants growing, we saw the trees going 50 metres tall, the emergent layer, the buttress roots. We looked at the sloth, or the sloth as David Attenborough would say, that is camouflaged and moves slowly for predators. Adaptation of plants, animals and cold environments. We looked at the polar bear, which is very, very fat to keep its heat in. It's got that layer of blubber. It's white to camouflage. It has small surface area to volume ratio in terms of its ears to retain heat. The plants, because it's very, very cold, they have a waxy surface to reduce water loss. Opportunities and challenges. Why on earth would people live in Svalbard? We said because of fishing and tourism. But why is that bad? Why is it hard? The challenges, well, accessibility, the water's frozen. It's also difficult to build infrastructure. Think about the pipes. Water pipes would just get frozen. Managing cold environments, you've got action by governments. You've got that Trans-Alaskan pipeline, which is raised so animals can migrate. Then coasts and rivers, mass movement. I didn't go over mass movement. Give us a shout out now if you want us to go over it. Miss Morris is shaking her head, no one's mentioned it. Landforms of erosion, cave arch, stack stump, upper, middle, lower course characteristics. We've been through that, V-shaped valley, U-shaped valley, lower course. Effectiveness of river management, Boscastle. We said that the car park, here's a car park was raised to prevent those 50 cars washing out again. And along the river, they have those modern bridges. That is what I thought was going to come up. That was me going through it. Please subscribe to my YouTube channel. Is there any other questions, Miss Morrissey, before we log off for the evening?
No other questions.
Nope, superb.
Ladies and gents, if you have watched all of this, my advice to you would now, especially if you've been in maths after school, is get yourself logged off, go and get your tea, chill out a little bit, no pressure. We will be seeing you for a booster tomorrow anyway. If you do have any more dying questions which you're desperate to ask and you're thinking, oh gosh, I wish I need to know this, either grab us in the morning, or if you are that desperate, do send myself or Miss Morrissey an email. I hope this has been useful. We will be asking for feedback to see whether or not to do one for paper 2 and paper 3. Enjoy, ladies and gents. Have a lovely... there is one more thing. There is one more thing. Bear with. Let's get rid of that. That is, ladies and gents, don't stress, do your best and forget the rest.